Welcome. Today, Chris and I are going to tell you about some of the exciting things going on in the CIRCT project, which is a project for developing hardware tools. So quick roadmap. We're going to talk and get on the same page about what hardware design is, how it's evolving these days, and then we'll introduce the CIRCT project, talk about some of the interesting things that hardware brings to compiler IRs, how we're pushing the boundaries of MLIR, and how this is being used in production at Sci5. So, hardware design. If maybe you took an undergraduate class and did some hardware design, this might have been the last time you saw it. And you might think it looks something like this. A hardware designer writes some program in this weird language called Verilog. I will acknowledge VHDL exists, but we're not going to talk about it anymore this talk. So a hardware designer is writing something in Verilog, decides that it's probably good, needs to run some tests, loads it into a simulator, writes a test bench, runs it. Looks good. Maybe this is really important, so we stick it on an FPGA, test it there. Looks good. Package it up, run it through some vendor tool, send it to a foundry somewhere with a really big check, and you get back an ASIC, right? Nice and straightforward. Well, unsurprisingly, this isn't really how it works. Hardware design is a big process. There's a lot of things that need to be designed, not just the logic. So there are a lot of other disciplines, disciplines and subdisciplines involved. Someone has to lay out power. Someone has to actually figure out how the chip is organized physically. And all of these things wind up with different little languages and tools and workflows. And throughout this process, there are a lot of verification engineers, right? Everything needs to be tested because mistakes are so costly. Now, each of these disciplines winds up needing different workflows, different tools, and all of these have to work together to get you a successful hardware design. And part of this, the reason for this is, as I said earlier, there's a lot of things to design. There's a lot of levels of hierarchy in the design. So you wind up with different disciplines. Someone may be caring about how an SoC is designed, what transactions exist, what buses exist, how power is managed through the chip. And that's a very different discipline than how you actually design the logic of some particular component or implement an algorithm. And that itself is really an abstract thing. What happens is we have gates and transistors. So there's another layer of abstraction there that someone has to deal with. And that's great, but real chips are not just abstract graphs of gates. They're actually physical artifacts that someone has to decide where everything goes. And that brings in new concerns about signal strength and timing and delays and power and a bunch of other stuff. But that's great. These things also are not implementing just simple gates. There's libraries of things from foundries and vendors that were designed for particular processes to give you nice optimized implementations of different constructs. So there's a mapping process there to stuff other people have designed, and someone needs to manage that. And so the net effect is you have a lot of disciplines that are interacting, and there's not really a single tool that unifies all of this. These are suites of tools and suites of workflows that are all mixing together to give you a real chip in the end. Now, kind of at the center of this is Verilog. And the reason for this is the design language, at least the one we're talking about today, that the design was originally written in and on which a lot of these other flows directly operate. Verilog is a fascinating language. It's really big. It's really verbose. But for our purposes, one of the important things is that it's serving several different communities. So there are really different subsets of the language that different tools support. And even tools for a particular use of the language, like synthesis, may not agree on what parts of the language you can use for that purpose. So there's all sorts of interesting compatibility issues just from the language features you use that arise. But because Verilog is the core of this process, it's really not just a design language. It turns out to be this medium of exchange between tools. It turns out to be an IR. So we have to think about this process as having these core IRs that are being used by lots of tools. And what do I mean by the IRs being used by tools? So a lot of these parts of the design process don't fit in Verilog. Verilog can't represent them, so they wind up being extra artifacts that are on the side in different languages, or annotations to non-standard annotations to Verilog, or very commonly, programs that you write and are executed in the context of a particular tool that are written against the internal representation the tool has of the Verilog you fed it. So this means that in a design, you wind up with lots and lots of pieces that need to come together to actually successfully produce a chip. Now, one thing about the hardware world that's interesting is hardware is an expensive endeavor, right? Actually making an ASIC costs a lot of money. And that has tended to mean a lot of the tools for doing so are very proprietary and very expensive because it's not a huge community. There's a lot of movement lately in getting a large, broad set of open source tools that really lower the barrier of entry into this realm. So there's a lot of interesting and good work that Chris is going to talk in part more about. Chris.
All right, thank you, Andrew. I'd like to talk about some of the changes that are happening in this ecosystem. Next. So one of the cool things that's happening is that as systems and chips get more complicated and bigger and billions of gates, people are reaching to higher levels of design abstraction. And so one of the things we're seeing today is that hardware is becoming cool again. And the academic and other industrial research groups are looking to improve the way that we design hardware. Now, there's dozens of different approaches here, including high-level synthesis and a bunch of other things like that. But for today's talk, we're going to talk about the approach that Sci5 uses as an example of this, next slide, which is an approach called generators. Now, here, let's talk about the problem, one of the small set of problems with Verilog. One of the problems is that the metaprogramming facilities in Verilog are very weak. Imagine C++ without a powerful template system, right? I mean, that's kind of what Verilog and System Verilog were like. Verilog is also verging on the untyped part of the spectrum, and so it's very easy to have bugs that aren't detected by the tools. Also, often you want to have tooling around the designs that want to interpret Verilog, but if Verilog's a 1,300-page spec, you can't just parsing it in the first place. It's very difficult. Next. And so one of the things that people turn to is they say, well, okay, instead of manually creating the Verilog and writing it out in VI, I will actually use an API to generate the Verilog for me. And so this is a very familiar approach you see across the ecosystem. It's like, Bison, for example, or even our friend TableGen is about saying, hey, how do we raise the design abstraction for my problem and use a meta language so that I don't have to write the underlying thing directly and as verbosely as before. Next. And so Chisel is an example of a generator framework. And what Chisel is, again, instead of writing things like System Verilog or IPExact or other of these canonical formats directly, what you do is you use a domain-specific language embedded in a normal programming language. In this case, that language is Scala. And so the hardware designer writes a bunch of Scala code against an API, and they use the OR operator and creates Verilog modules and things like this with an API that then goes into this big box of Chisel, which chomps on it, does a bunch of lowering and other transformations, and then out the back comes Verilog. And because Chisel is a typed language, because there's high-level APIs, you get a lot more safety and you get a lot more design reuse and productivity. This is something that we at Sci5 use pervasively, and so this is very much a production system. Next. So one of the cool things to me about Chisel and about these generator frameworks is that as they're getting more complicated, they are becoming compilers. And so literally, Chisel has a whole compiler stack within it called Fertile, and it has this Fertile IR. And the reason that this got introduced is that as Chisel got more and more complicated, the lowering from the high-level design abstraction the programmers were thinking about and the ultimate Verilog, that gap got so big. And so you can see this in many high-level languages. I look at Clang, for example, the lowering from ASTs to IR got progressively more and more and more and more and more complicated. And so it gets more and more difficult to rationalize. Well, the chisel engineers saw this problem and introduced an IR that you could then do progressive lowering. Now, one of the things I'll observe here is that this idea of use an imperative programming language to stage a graph and use that graph to target multiple different backends is something that cross-cuts domains. This isn't a hardware thing. I mean, if you look at the machine learning world, this is basically what Keras is doing, where you use a Python API and it stages out a graph. And so a graph of convolutions and matmulus. And so one of the nice things about this is that many of the approaches in the ecosystem are applicable to all these different problems. Next. And so the other cool thing about compilers is that because it's a real IR, compiler IRs are designed to make it easy to analyze and transform and build tooling around it. And so one of the things that Sci5 and the Chisel ecosystem has been great at is building really important tools that are often locked up in these proprietary tools. So for example, there's a design for test thing that happens in the hardware world. And some of the tools for this are $1 million for a license. We can implement that as a compiler transformation in a couple of months with one engineer. And that's because we don't have to start from parsing Verilog and solving all these hard problems. We have a pre-designed IR that is easy to analyze and transform. Next. Now, open source tools are super awesome. I think we all love open source and understand the impact that it has on the world. But one of the challenges here is that the open source hardware design world is super fragmented. Each of the communities is building different parts of the tool stack. They're tackling different problems. They're often tackling one small subset of the big picture, and they're doing it with different code bases, often which have evolved over the course of many years. And while many of us use a lot of these open source tools, the fact that they don't share code makes it very difficult to add new features or extend things or make cross-cutting architectural decisions. One of the other big problems is that, as Andrew pointed out, Verilog isn't a great IR. And Verilog and all of its cousins you have to interoperate with have pervasive redundancy, and there's no single source of truth. And so nobody is really tackling that problem either. Next. Which brings us to the big idea. So the big idea is, hey, if we learn from this LLVM thing really helped cause an innovation explosion in tools and applications for compilers by having a library-based design and having a modular and stacked out set of infrastructure that could be used for everything from a OpenCL JIT compiler thing to a really fancy vectorizing C compiler, right? Next slide. And so we think that we need this for hardware design. This brings us to the CIRCT project. So let's dive in quickly and talk about what that's all about. So CIRCT is an LLVM subproject. You can find us on circit.llvm.org. And the whole idea is to take MLIR and build an LLVM philosophy for hardware design set of infrastructure. And so what CIRCT provides is a vertical on top of MLIR, which then allows us to model hardware, build and tackle the verification problem. And a lot of the value system from LLVM, of course, comes directly over in terms of tooling and quality and production testing and all that kind of stuff. Next. And so one of the other big problems that I see in the hardware design tools community is that often these technology silos of the different tools that have been built up over time mean that there's fragments of the community that don't talk with each other. So one of the things that the CIRCT community is doing is it's fostering an open discussion forum where people can come together, give tech talks on the research or the systems they're doing. And this has been a great way to pull together this really important but very small community together into one space. And we've been learning a lot from each other. If you're interested, you can join our weekly meetings or even just lurk or watch some of the old videos. You'll see lots of interesting technical topics and other design discussions about IRs and this kind of stuff. Next. But fundamentally, CIRCT is about building cool stuff that people can use. And we're getting to the point where things are really interesting. And so the CIRCT project has a whole bunch of MLIR dialects, including a full implementation of this fertile compiler that we were talking about before. We'll talk about later. There's a bunch of other folks that are working on using CIRCT for their existing projects, including the Magma Python hardware design language, the Moore front end, which is a Rust-based system, LLHD. And there's a lot of interesting people that are getting involved, doing cool things, and it's really exciting to work with great people. Now, one thing we'll talk about later is that the part of the problem we're tackling is what is called the front end part. And so we haven't tackled the place and route and other physical design pieces yet. Next. So one of the cool things about CIRCT is that it is using MLIR in a way that nobody else does. And so we are pushing and causing some interesting extensions, changes, and running to boundaries with MLIR that are a little bit different. For example, generating a text file from an IR is a different set of concerns than generating machine code. And so this is pretty cool, and we hope this is interesting to many people. So Andrew, can you tell us about hardware IRs and what they're like?
Yes. So fundamentally, hardware isn't software, and that impacts the IRs for compilers in some interesting ways. We'll talk about a few of them. The first one is execution model. Right? Fundamentally, hardware is based on this convergence of electrical signals, not on atomic operations that are interleaved in some order. So what this means is at the lowest level, your logic is not a DAG. So it's not trivially SSA. For a lot of design, we hide this fact behind abstractions so that humans can program these things. But if we're making a compiler in this space, this is a concern we need to deal with. So there is a general support that was added to MLIR for this. And this is regions that are non-SSA form, right? You can have uses that aren't dominated by their definitions. I took the example from the previous slide. Here it is in CIRCT. I've highlighted the back edges in this graph. And as you can see, we can correctly code gen this, run optimizations on it. And this is a really useful construct, which is far more applicable than just hardware. Lots of domains are more naturally represented as abstract graphs than DAGs. So if this describes your domain, give this a try. It might simplify your modeling considerably. This work was pushed by Stephen, who's giving a talk specifically on it. So if it sounds interesting, by all means, go to his talk. It should be very interesting. Another really interesting difference between hardware and software comes in the modeling of instances of modules. So in hardware, you often think about modules. These have inputs, they have outputs, they encapsulate logic. Boy, this sounds a lot like a function. And they can instantiate other modules, right? So naturally, you get some graph of instantiation called the instance graph. And this looks a lot like a function or like a call graph. But there's some really important differences. In the hardware world, the instance graph is actually just a summary of what's going on. It's an abstraction because each leaf in the fully expanded version of that graph is actually a physical thing that permanently exists. Unlike a call graph where you're kind of describing ephemeral behavior of your program. So what this means is because these are real things, all of these leaves in these graphs are real things, we often want to talk about individual ones and give them properties. So for example, one particular instance of one particular module I may want to lay out on my chip at one spot. That only applies to that instance, not any of the other ones. So I need a way of talking about one particular thing in the instance graph. So how do we do that in CIRCT? We encapsulate this notion of paths through the instance graph as a path operator, which gives you a sequence of steps through the instance graph and then gives you an object that you can use in other operators that talk about the instances or talk about anything really that is instantiated, wires, registers, whatnot. But this really gives us a unified way of capturing these context-sensitive paths in the IR and attaching them to anything that wants to use them. This comes in very handy in verification. So as we said earlier, verification is a huge domain in hardware design. And it's very desirable that the thing you verify, the code you verify, is exactly what you pass to the synthesis and later tools. There's not a notion of, oh, I'll make a debug build or I'll make a release build with assertions, right? Because that's then verifying something that's not actually what you are building. You're building. So the languages and the compilers have to deal with this. And Verilog gives a few mechanisms to deal with this that have a lot of impact on the IR. So what you want to do is be able to move all of your tests into basically separate libraries that in simulation are linked into your library with your main design unmodified. But that means like somehow I have to get access to all the variables and stuff in my design without modifying it. So here I have a little example in a test bench. And this test bench, you'll see, has these very path-looking things which allow the test bench to reach into the design and start reading and writing values without modifying the original design. So this mechanism gives you a way to build these side libraries. Now, this is really annoying from a compiler perspective, because this means that the public API, or what's public, the public symbols of your design are essentially anything that might have a name, right? You don't know what a later tester is going to want to get access to. So suddenly every name is public, which is very different from your classic software world where you just have a few symbols floating around. So how do we deal with this? There's a couple of ways we have to deal with this. One is we need a compiler-friendly way to be able to refer to elements in the design. And for our own sanity and optimization reasons, we don't want every possible thing that you might be public to always be public. We actually want to be able to distinguish public and private. So what we do is we allow basically any declaration-like thing to optionally have a symbol attached, which says, I'm public, I need to be preserved. And then we have a mechanism for naming these. These look like nested symbol tables. They aren't pure MLIR symbol tables for reasons I won't go into. But this, in the combination of paths, now lets us refer and preserve things we need to preserve. The other thing Verilog has that's used extensively is basically action at a distance, but for instantiation. So what you'll want to do is say, I have this module I want to test. I'm going to put all my debug code in a different module, and I will instantiate it in the thing I'm testing and pass all the signals I want into it so I can monitor it remotely. But I don't want to print the thing in the module, because that would be modifying my original code and having stuff that isn't actually going to be synthesized. So Verilog gives you this mechanism to take the instantiation and put it somewhere else. So we do this by sticking normal instantiation in the module so that we preserve all the names and data flow for analysis purposes. But then we have this other hook, which is a bind statement that the user can put wherever they actually want the emission to occur. So in this example, I have some module I'm testing, AB, and you'll see that this instance of debug stuff doesn't actually appear in the generated Verilog. It appears in some other file where the user wanted, which remotely causes an instance to have happened in the Verilog when you actually link in this other Verilog. So that's an interesting mechanism. Another thing we really care about is files for all the various tools that are running in our design. So, Chris said that there's generators are pervasive. Internally, our flows often will generate code that needs to collect some data and pass it off to a generator. There's all this other tooling around design that all take their own input. So we need a way for the compiler to generate all of this stuff in arbitrary formats. So here's an example of a real thing we do, which is early in the pipeline when we still have memory abstractions and stuff. We walk through the design, we find all of the memories, we collect all the data about how we want how they need to be generated, and we spit them out. And we spit them out into this file, which is used for test benches to read and write memories. It's used to drive vendor process-specific memory generators to get optimized memory blocks, et cetera, right? So this kind of summary data exists all through the pipeline. So how do we do it from the compiler? And how do we do it in the presence of optimizations? So what we do here is we really allow passes to simply embed this text that they want to generate verbatim with a verbatim op. And verbatims have text substitution. So they're basically like arbitrary printf things, but the substitution is smart, right? You can pass in paths, you can pass in symbols, and then at emission time, we can resolve those to the actual names that were used during code emission or whatnot to give you how, your description of your temporaries temporary files, but in terms of what was actually generated. And the second part is we need to be able to control what output files different things go to. So pervasively through the top level, things can specify, I want to go to this file or to this directory. And then the emitter will emit things in the right spot. So we use this extensively to deal with all of these kind of sideband random stuff that exists in real flows. So back to generators, these are pervasive, even before our modern, kind of these modern languages and approaches, these have existed, right? Vendor tools are full of generators that you run. But then the question is, how do you deal with this in your design? There's two main approaches, and often you see both of them used in the same design. One is to say, look, I have this generator, I run it, it produces some output. The output now has to go to the next tool and be linked in or processed or whatever. Boy, this looks like a build system problem. And so the first common solution is to embed this in the build system. And this is great because it at least captures how things are being generated specifically. But it turns out a lot of EDA tools are either not entirely trusted by their designers or are really hard to make deterministic. It's surprising how many asterisks you have to pay attention to actually get deterministic output. So a reaction to that is to say, look, I'm not going to trust the build system. I'm just going to have my designer run stuff, the generator till they get exactly what they want. We're going to check that in, and then there's no questions about what code we compiled for the chip. And that's great until you don't have that designer anymore and you find the documentation is lacking and your data center is having large numbers of failed somethings because you can't replicate the bug because you don't know exactly what code was used. I've seen this happen. So what do we do? How do we deal with this? So this is very much a work in progress, but what we're trying to do is embed the knowledge of generators into the IR specifically. So when the compiler needs, it knows how to say, resolve this thing by running some program or pass or whatnot. And this right now can deal with a lot of the simple generators we have, like the memory example I gave. But long term, this gives you a lot of power, right? So imagine you're doing an SoC and you have a bunch of modules and you need to actually construct the interconnect for them. That generator is not just here's some parameters, spit out some new Verilog. That thing has to dig through the circuit, rearrange the structure, add a bunch of stuff. But it can do that because it can start looking at the circuit when it is generating. So this is an interesting place we are pushing on the system. For some of the other ways we're pushing the boundaries, I will turn it back over to Chris.
Yeah, so one of the fun things about doing weird things is you get to learn some things. So let's talk about generating source code from MLIR. Next. So one of the things that we've struggled with is that we're generating Verilog source code. And the reason we do this is that we have all these complicated systems that then produce Verilog, and we as Sci5 take that Verilog and we sell it to our customers, right? And so when your customer is looking at the Verilog that you sell them, you actually want it to be pretty good, at least not embarrassing, right? And so suddenly now you start to care about the quality of the code and the formatting and even basic things like that. But moreover, we have to generate things like macros and if-defs and comments and other things like this in the generated Verilog. And so we need to have the ability to manage that and make sure that it is good. And this is not something you see in a typical compiler, because typically the first thing the parser does is throws away the comments and gets rid of the if-defs and goes. And so this raises some interesting challenges. Next. So the solution that we've converged on is a set of layered dialects in MLIR. Anybody who's worked with MLIR may not be surprised to hear that. One of which is the system Verilog dialect. The system Verilog dialect manages a lot of the textual things that system Verilog can do. And so, for example, we have the verbatim node that Andrew was talking about before. So verbatim node is a great way to have a comment. We have side effecting and non-side effecting versions and like all kinds of fancy things, but allows you to drop in arbitrary system Verilog code directly if you'd like to. We also have if-def nodes, which are take a region and then it semantically is a conditionally compiled thing, which prints out as an if-def. One of the nice things about this is that by exposing these things things and defining these things in the IR, that which you can represent, you can transform. And so we can do syntax optimizations as compiler passes. And we can say, hey, if you have two if statements, behavioral if statements on the same condition, or you have an always block on the same clock, we can actually merge those together into one unit, which then allows recursive simplification and transformation of the IR, just like you do with a normal compiler. But now it's applying directly to source code, which has worked out really well. Next. One of the other challenges we have is that while we have some of this behavioral and syntactic set of problems, the core set of what you're trying to do in a IR for hardware is be able to represent the logic. And so another dialect we have is this combinational dialect for combinational logic and some sequential stuff and some other things going on. And so we want to make it so it's really easy to use SSA and be able to do analysis and transformation of the logic. So you can do your people optimizations and all this kind of stuff, right? On the other hand, Verilog is kind of a pain to generate. And so Verilog, you of course can't, if you have a multi-use expression, you can't output that syntactically in line in two different places. So you need a temporary. Verilog has constraints where you can't subscript into all the things. And so sometimes you need other temporaries. Of course, we want it to look pretty. And so we want it to wrap nicely to whatever line length you want. And you want to be able to get 3 space indents or whatever. You should totally be able to do that as a user. And so the CIRCT infrastructure allows both transformations to be easy to write and the IR to be easy to produce, but it handles a lot of that syntactic stuff for you, which is a nice relief. Next. So there's another challenge here, which is that, as we've been talking about, there's a whole bunch of tools in the ecosystem that we end up working with. Some of them are more rusty than others. And so they accept different subsets of the language. And particularly if you're trying to generate Verilog, you're trying to be a designer or you're trying to build a tool that generates Verilog, this is a real pain because it turns out that on one hand, there's a lot of different things you might want to generate. On the other hand, there's a lot of different kinds of tools and different users care about different subsets of tools. And so some people will say, hey, I only want the latest, fanciest system Verilog features because I'm using proprietary tools. Other people say I'm using this open source tool that's 30 years old and it doesn't support those features, right? And so one of the things that's valuable about CIRCT is it takes a lot of that complexity and encapsulates it in a common infrastructure. Next. So the way this works is we have something that's sort of like a target triple. So it's like a target feature string almost. And so there's a string that you can put on the MLIR module that says, hey, here's the set of policy for what I'm lowering towards. This thing then converts into a nice typed C++ object that then describes all the different constraints in a way that's easy for analyses to work with. And then we have a bunch of lowering passes that then handle lowering out the things that are not supported. So it's pretty straightforward. Next. And so the implications of this can be fairly profound. So one of the things that that not all tools support is this highfalutin concept of multidimensional arrays. And so surprising, like pretty much none of the open source tools support this. And so something like a multi-bit selection or multi-bit mux is very naturally expressed as a multi-dimensional array, which you then select out one of the arrays out of this thing. And so if you're using the default fancy lowering, you get the thing on the left, which is very syntactically concise. It efficiently synthesizes into good RTL or good designs. But if you don't, then you pass one flag and CIRCT will take that and it will expand it out into a switch statement for you, a case statement. And you get equivalent logic that's more verbose, but it's more compatible with different tools. And the cool thing about this is that the designer and the front-end author doesn't have to worry about this. This is something they get out of the box by leveraging the infrastructure that CIRCT provides. Next. Let's talk about lowering. So we've talked about the challenges of lowering in these monolithic passes. Andrew was talking about all these text files we have to produce and all these different things. At the top level, this fertile compiler thing has a fertile dialect on the one hand, which has a whole bunch of pretty high level abstractions and nice ways of describing the design intent of the system, like memories. On the other hand, you have something that gets much closer to Verilog abstraction, which is this hardware combinational and system Verilog sets of dialects. And so there's a lowering that happens. Now that lowering is really complicated. On the one hand, they both have muxes, and so that's fine. On the other hand, one has memories and one does not. One, in this process of lowering, we have to generate these hundreds or thousands of text files, and these are often domain specific, sometimes company specific, and having one monolithic pass that handles all this in one place just doesn't scale, it doesn't work very well. Next. So what we've converged on is we're taking advantage of the representational power of MLIR to be able to represent and hold code in multiple dialects in the same module. And so here what you'll see is that we've taken this monolithic set of low rings and broken it down into half a dozen passes where you say, okay, I'm going to take memories and black box them and generate both the loaded representation in the in the hardware design, but then I'll also generate a pile of metadata in the hardware dialect. And as you go through this, you can run many of these passes, which then become optional and configurable. And they're generating this metadata, they're generating the system Verilog interfaces and like all this fancy stuff. And then you get down to the point where everything, all the fancy stuff's loaded out, and you just have muxes and AND gates and things like this, and you have that final conversion. And this progressive lowering has been really nice to help us scale. Now, another challenge we face is that we are pushing MLIR to its performance limits, and this is because hardware is big. It's very typical for us to have half a gigabyte of fertile text input into our compiler, which then generates 300 megabytes or so of system Verilog output. Having 5 gigabytes of input batch is not uncommon, and so we face this question of how do we make our developers more productive. Next. And the answer for this is to make MLIR go fast. And so we've put a lot of work into making the MLIR data structures and memory usage, and we've been working with the community to help improve things. We've also been pushing parallelization into the compiler in a way that I don't think anybody else has done. We've even gone so far as to parallelize our parser and our printer, which was a huge, huge, huge win. And we've gotten really good results out of this. Next slide. Now, one of the concerns here is that while we've made tremendous progress, we still have a long ways to go in the MLIR and LLVM ecosystem. And so at the bottom of the slide, you can see a utilization graph on an 8-core laptop. And all that white space are cores that are being bored and not doing anything useful. And so there's a bunch of implications here and a bunch of future challenges, one of which is that this whole threading.h thing is not super great in LLVM. You don't have feature-based approaches. You can't support hierarchical parallelism. Function pass managers being parallel is certainly not enough. Going further, we have more difficult to parallelize transformations like lattice updates and like IP SCCP type passes. And over time, we're not just interested in constant time speedups. We're interested in algorithmic improvements like making chisel list monolithic, improving caching and distribution in the compiler itself, and really kind of pushing the envelope on compiler design here. Next. Do you want to take it away, Andrew, and talk about using this stuff in production?
Yes. So CIRCT isn't just a toy, although it's fun to make compiler infrastructure. We actually want to use it for real stuff. So let's talk about that. If you were to go download CIRCT today, one of the tools you would find is FurTool, which is a drop-in replacement for the fertile compiler part of the chisel pass that Chris was talking about. And we are deploying this internally to build all our cores and clean up a lot of other things in our workflows. And as Chris was saying, some of these are very big. Some of these are several gigabytes of source going through this tool, and that's generating thousands of output files. Now, changing compilers like this is a big risk when you do it, and so we're doing a lot of things to verify. One I want to briefly talk about was our use of formal methods. So one thing we're doing is we have a couple of approaches. We're taking randomly generated circuits and fuzzing our output by trying to do formal equivalence between our reference compiler and our FurTool. And we're doing this for randomly generated circuits. We're doing this for all of our cores internally and subcomponents thereof. And this has been really helpful for finding bugs, both in kind of interpretations of specs and in all of the really, really weird corner cases that exist in Verilog. So at your leisure, you can look at this real bug and try to figure out which of the differences between the code actually is the bug. It's probably not the one you think. I'll leave that as an exercise to the reader. But this has actually been really helpful for not just improving CIRCT and our code generation there, but improving our reference compiler, right? We have found bugs in both, and that's been really useful. Now, as much as formal methods have been really helpful, there's been some places where they break down. The most annoying of which is when dealing with this, where places in the spec where different implementations are permitted. So, for example, since these formal tools are operating on a very low level of abstraction, they're operating on at the Verilog level. When you have different behaviors, things stop matching, right? Like if I have an alternate implementation of a memory, even if it's correct according to the spec, it is not formally equivalent, right? Like this is equivalent to taking two different C++ libraries and comparing the internal states of the implementation while it's running. Like they are not going to match, they are different. So then, on a case-by-case basis, you have to say, okay, what matters more, the spec or the old implementation? And since Chisel is really a one implementation world right now, you have the other concern of how much are designers depending on particular implementation choices rather than the specification. The other place a lot of these formal methods break down is once you start optimizing state elements like registers or memories and changing them, they tend to break down in what they can prove. So we have to be really careful there. Now, one of the reasons we went down this path, though certainly not the only reason, is to speed up the inner loop development time. How long does it take to go from a designer changing a line of chisel to being able to see the results in a simulator? And there are several tools along this path. So, this particular replacement of Fertile is not sufficient to really get this time completely to what we want, but it was a very big component of that. So what we're seeing for a lot of our interesting cores is around a 10x improvement in the time it takes to run the Fertile portion of the compiler. And this happens to be really useful along with some other gains we're seeing. So we're actually seeing memory reductions of around 90% over the reference compiler. And those two things put together really allow designs to scale up in complexity. Our most complex designs we are working with are starting to exceed what some large portions of our build cluster can actually deal with in memory usage, let alone they might take a day to run. So it's really critical that we get this resource usage under control to be able to scale up our designs and be able to meet our expected development. One thing that's really nice is as we start getting more information properly structured in an IR, this allows us to start cleaning up all our build systems. So remember how I said there was all sorts of files for passing information between tools. A lot of those are an artifact of not being able to query Verilog, because Verilog is too nasty to parse. By the time you get there, you've lost some high-level stuff. So we can do a lot of cleanup there. And our main reaction so far is, when can we get this, and what else can you do? So for what else you can do, I'll turn it back to Chris.
Cool, thanks, Andrew. Yeah, so this is just the beginning, and it's really exciting to see all the different opportunities we have ahead of us. Next. Oh, there you go. Okay, so just to level set, we started by talking about the big problem here. And so far, we're talking about this one little tiny part up in the front end of helping people with high design abstraction and complexity. But there's this huge world that we expect to tackle over time. Next. And so when you start thinking about this space, you start thinking about all the different opportunities for pulling in power modeling, SOC assembly. We eventually will need a Verilog parser that's Clang-like and really high quality so we can build new kinds of tools. There's a lot of opportunities for formal methods, all the physical design stuff, all the new different better abstractions that we can invent for like doing high-level design and design capture. There's just this tremendous opportunity that we're looking forward to and building on top of high-quality infrastructure. Next. So one of the things that I'll leave you with is that, it turns out that software is a really big and important problem for hardware design, and you can't have one without the other. And the problem is that nothing has ever been able to handle both hardware and software. Next. But wouldn't it be great if there was a compiler framework that also understood this whole software thing? And if you bring these two things together, don't you think interesting things could happen? Next. Well, so I'm really excited about this whole space. If you're interested, there's another short talk by a bunch of folks in the CIRCT community talking about different subparts of this project, and it's a really exciting time in space. Next. And so to wrap it up, CIRCT is all about saying, let's take a look at this hardware design thing. Let's apply the best practices in compiler design and new technologies like MLIR. We think that people working together on shared code with high quality implementations will really change the world. So thank you, everyone.
Chris and Andrew. So I'm Megan and I work with Chris and Andrew, and I'm here to take some of your questions. So we do have one question so far, and if you'd like, you can enter your questions on the Q&A. So the first question we have is, so MLIR has better parallel execution than LLVM core. Would an approach to move more optimizations to MLIR converge faster than trying to make the LLVM IR modules more amenable to parallel execution?
I'll take this. So myself have been working on trying to get LLVM be parallel for many years, and I consider it to be a hopeless quest at this point. The problem there is that the USDEF chains in LLVM span the entire module, and so you can't have parallel function passes and other very simple things like that working in LLVM. So I don't think that that's a solvable problem in LLVM given the way it's designed. And so I think that's a question for us as a community of when do we upgrade LLVM IR and maybe use MLIR for some of those mid-level optimizations. And I think that's a hugely complicated topic that we can talk about in a breakout room or something.
All right. Thank you. So yeah, again, don't forget to ask your questions in a Q&A. I guess I have a question for myself, but so let's say we're ultimately successful in lifting the hardware design into the 21st century. So how do you think the world will be different? What new products and technologies are going to be enabled by this effort?
Sure. So I think a lot of this goes back to the comment earlier on that there's a really high barrier of entry. It's really hard to experiment in this space and do research and invent new stuff. And this is in part to address that problem. So we're seeing a lot of very interesting developments, alternate ways of expressing hardware, interesting mixes of hardware and software, rapidly prototyping and developing kind of domain-specific processors. All of these are relatively hard now, but hopefully having some better tools and better infrastructure will let the community really explode in this area.
All right, thanks, Andrew. So another question we have is, isn't the right time to bump the C++ version in LLVM to C++ 17, or sorry, isn't it the right time to get more parallelism directly from the STL with algorithms and parallel policies?
Yeah, so I mean, I think that there's two questions here. One is it the right time to go to C++ 17? Some projects like Flang and CIRCT already use C++ 17, and so I don't think that it's really a question about, well, I think the question there is, when can LLVM, Clang, and the other more widely used projects take on that dependency? And that's really a tools question, and I think discussing that in LLVM Dev is the right way to go. I don't have an opinion about that. I will say that using C++ 17 does not magically solve the problems we have, because we do have parallel for loops, we do have threads, we do have basic parallelism constructs. The issues are that we need higher level parallelism APIs, and we need other things like thread pools and stuff like that that are more efficient, and C++ 17 doesn't provide a lot of that kind of stuff. The other thing is concurrent data structures and other higher level stuff that isn't quite in the C++ spec would be very helpful. Finally, it comes down to you need to parallelize the compiler algorithms. And we've done quite a bit of that in CIRCT. And so we've parallelized the parser and things like this. And so that's a lot of work. And that's a lot of work that we in the LLVM community haven't done before. And so there's some just kind of open research on that. If you're interested, please come and start a discussion on CIRCT forums, because it's actually quite interesting to think about the trade-offs in the space, and there's a lot of good work that could be done that are transferable to other domains.
All right, thank you. So maybe this is a question for Andrew, but which build system are you using with Virtool to work with all the different files that are corresponding to all the hardware components?
So that's interesting. Internally, we're using several build tools systems. There's a bunch of just plain make stuff that is still in use. There's a public project you can go find from Sci-Fi called Wake, which is a higher level build system with caching and stuff like that. But really, like, the core of the build problem isn't so much what we're using to execute stuff, though that has implications for efficiency and caching and stuff, but all of the side channels that have to exist to run all of the workflows attached to the build.
Yeah, it comes down to what is your design truth, right? Where if you take your design source of truth and you start replicating it both in the hardware design language and in the build system, then whenever a change to design comes down the pipeline, which it happens all the time, you're onto bugs, mismatches, coordination issues, and things like that. So one of the quests we're on is to get to a single source of truth for designs. This spans hardware and software, and there's a bunch of implications for that.
All right. So how many levels up the stack would you like CIRCT to reach? Do you envisage a future Keras-like Python framework? And if so, what are the main challenges to this that you see?
Sure. There are, I would say right now, ambitions are pretty unbounded. Once you have higher level information about your system, so for right now, for example, Verilog doesn't really capture anything about SoC design. There's a lot of interesting things in SoC design. You know, a simple example is, like, how do I shut off parts of the chip and power gate them and control their clock? We can't deal with that. But if we could represent that stuff, then what could we do, right? Okay, so now we actually have a representation that the compiler can read. Suddenly, there's a lot of other collateral, firmware and software and drivers and OS stuff that possibly could be directly inferred from these higher level representations. So it's not really just about like moving up the existing stack, but enabling new interesting areas for the compiler to be able to simplify the life of developers.
Yeah, I completely agree with Andrew. And if you haven't worked on this role, it's really hard to understand how bad it is, right? So Verilog can't express the idea of connecting two buses together. Instead, you get 591 wires, which hopefully you get the names on the signals right, or else really bad things happen, right? So the level of abstraction is really challenging here. The other thing I'd say is that what I would love to see happen is, as the front end part of this gets built up, and then you start building a new circuit native simulator or circuit native place and route tool or circuit native these things over time, going through Verilog stops being necessary. And if you have native tools that all work together on a higher level IR, well, now you can do a lot of really interesting things because you capture design intent in a way that those tools that come post Verilog have never been able to have access to. And so now you can have much faster simulators. You can get much better control over the quality of results. You can have much less tickle in this whole mess. There's like all these opportunities to make the world better. And the key to me is build things one step at a time and make sure that you're always making progress and are grounded on production.
Okay. So we talked about the non-DAG problem. So non-DAG data flow in LLVM is possible, but only with PHIs, block arguments, and MLIR. Why is that not sufficient for representing graph-like data flow in CIRCT?
Do you want to take this, Andrew? Sure. So a lot of it, there's a lot of representational differences, and we don't, because of how we're dealing with system Verilog now. It's a very close match to Verilog, so we don't have the same kind of data flow that you would expect from kind of a normal branch-based execution. Some of that potentially could change with alternate representations, but for, I think, more details on what motivates this, by all means, go to Stephen's talk.
Yeah, so I mean, one of the key things comes back to Andrew's initial point about this is not, you don't have a program counter executing basic blocks. And so we don't have basic blocks, and so we don't have branches, and so we don't have feed nodes, right? And so what you have is you have generally one top level thing with a bunch of logic that's all mixed together, and they're wires connecting things. So it's a pretty different domain.
Okay, well, I think we're out of time for questions. So there are a few more questions left, so please come to the CIRCT mailing list and ask your questions there. Thank you so much, Andrew and Chris, for sharing today.
And thank you, Megan.
Thank you all.